So when I was asked by Amanda, what do you want to talk about? I wrote down a title for a talk that I was kind of excited about. Encoding heterogeneity through constraints in multi-robot teams, and I even had an abstract to go with it. Because there's some vague ideas I had been playing around with that I really saw a clear path how one would go from these vague ideas into some, I think, rather interesting results. So, at the time of the writing of the title and the abstract, it was aspirational. The biggest change between then and now is that I added a question mark at the end of the title. It's not an exclamation point yet. It's a journey. I'm on a journey, and we're getting to a point that I think is potentially really interesting. But the journey is a little bit odd, to be completely honest. I'm going to start by talking about the Robotarium. I hinted at this yesterday. I'm going to talk about it because I like it, but also because it actually follows the narrative that I'm trying to pull off here today. I'm going to take from there and talk about sloths and really slow animals. And in fact, tee up Ron Arkin's talk a little bit later. And then from there, I'm going to slide into a rather technical piece on composable barrier certificates. And along the way, I actually have a mathematical formulation of the meaning of life. So, tall order, 20 minutes, strange route, let's start. I do swarm robotics, right? And I have a lab that I feel really good about. It's taken me 15 years to get to a point where the gap between theorem, simulation, and deployment is very long. That's very small. But at the same time, it's been bothering me more and more that you need that kind of infrastructure and resource to truly be able to deploy teams of robots rapidly. And a few years ago, I went to a swarms conference where there were a bunch of biologists that gave really good talks, and all of them, the last slide was a picture of a robot where they said, this could be applied to robotics. And I started wondering, why isn't it applied to robotics? Why aren't we seeing this? And what I set out to do was solve that by building a remotely accessible swarm robotics research platform. It's the Robotarium. It's a terrarium for robots. We started with the Roboquarium, but we realized that there's no water, so it's not an aquarium. And my humble ambition is I want 1,000 research users. This is not an educational platform, this is a research platform. Part of it is, there are so many people that do good work that don't actually put it on robots. Part of it is that we're, I think, spending time on non-productive things as well. Meaning, we're implementing the same thing over and over again. We're basically, instead of leveraging each other's contributions. So I got one of these MRIs, major research instrumentation grants from NSF to build it. And the first problem we had was, you know what, Gaurav is a good guy. I genuinely think so. But if he's putting his code on my robots, how do I know that I can trust that you're not going to break it? Maybe you won't, maybe you will. So we added a simulation layer to verify things, but at the end of the day, you want to be able to test weird algorithms. And since momentum is mass times velocity, if you make the mass small, Gaurav is going to break fewer things. So we've started with really small robots. So here is a non-robust version of the rendezvous problem. And robots are just driving smack into each other. And we've been playing around with, can we actually break them? And indeed, we actually can. If you go all in, straight. If Gaurav's algorithm is telling the robots to just go straight into each other, they do break. So we need to fix that. I don't want you to break those things, even though I just don't. Let's leave it at that. So, what do? You have to wrap collision avoidance kind of mechanisms around Gaurav's control programs. The problem is, as we go up in densities, we now deploy 25 robots on it's basically a table tennis-sized area. If the collision avoidance algorithms are too intrusive, or if they're basically any kind of 1 over the distance squared kind of collision avoidance algorithms, they will completely take over the behavior. So what we really want is for people to be able to try their code as much as humanly possible and then just avoid catastrophic events. So we started looking at what are truly the minimally invasive way of avoiding collisions. And it turns out that you can actually formulate this quite tightly. So here are 2 robots. They're about to collide, but the arrows are green because it's still possible, humanly possible for them to avoid collisions. Another way to encode this is to say, well, here's a set of safe states, joint state space, right? As long as you're in the interior, you're fine. On the boundary, you have to do something evasive, and on the outside, there's no way of not colliding. And another way of encoding this is with level sets. You're saying as long as H is positive, you're fine. Here, you have to do something, and here you're bad. Right? So with this, you can write down a very, very simple optimization problem instantaneously that says that Guara wants the robots to do U sub nominal. I'm going to say, you know what, you get to do U. It's going to be as close as possible, such that we're safe, such that H of X is positive, and this is really a pairwise constraint between all robots, and it turns out that if you have double integrators, this is what this constraint needs to look like. So this is something one could do. It's nonsense, but you can do it. And the reason it's nonsense is this is a control. You're minimizing over a controller subject to a constraint that is just a function of the state instantaneously. So these are completely uncoupled. So the way you couple this is to not call this a level set. You call this a barrier function, and you write down something called a barrier certificate, which is the dynamic equivalence of this. And then you get rid of all the pairs, because there are too many, you only pick the right ones. So the way you encode a minimally invasive dynamic collision avoidance strategy is simply through this, it's called a controlled barrier function condition. Right? And this gives you a provably forward invariant safety set, which is code for if you start safe, you stay safe, guaranteed. So the way this would look is, you know, we've tried it in a bunch of different settings. So you have 4 robots, they're asked to swap positions, they're just going for it. Right? That's failure. So now we just wrap these barrier certificates around it, and they're not told to go counterclockwise or in any way, they just solve this problem. What I like about this is that it looks right. So many times when I look at robotics things, it's going, yeah, it did it, but it didn't look like the way I would do it. Here it's almost like people, and you can scale this up because it's not, you only have to worry about the robots that are truly close by. And the reason this works is that everyone is collaborating. So it's a shared responsibility. There's a lot of collision avoidance where you avoid the worst case, where you avoid, so all of this Claire Tomlin kind of level set stuff is avoiding the worst case. This is only avoiding the best case because everyone is collaborating. So what happens when you have a big bad robot that's not collaborating here? Oh no, the little guy said to. So it still works, but it's not minimally invasive anymore. We actually even did this in the air, which I think is cool. So here is a new video. 4 quadcopters is doing a death spiral, and 1 quadcopter is asked to just fly through it, and then they have to do this correction. So, point is, we can encode these constraints, and they're provably minimally invasive, and the way we encode them are through control barrier functions. They are very similar to control diagonal functions, but since they show up in constraints, they actually have a slightly different flavor. Good. So, we have some way of encoding constraints. Now, the next question is, what do sloths have to do with it? Well, apparently nothing. This is my commercial slide. So for those of you interested, the Robotarium is open for business. We have right now deployed 25 robots. There are 11 research groups to date that have used it. We have 85 remote, so these are the tech users that have been running experiments, and it's pretty exciting. But let's go to sloths. And the order will become clear in a bit. Me and Ron, Vijay and Amanda, we have a really fun ONR project with Mark Steinberg where we're trying to understand the value and characterization of heterogeneity. Fundamental. What is it fundamentally good for? How do we fundamentally measure it? How do we fundamentally design for it? And if you look at nature, nature is highly diverse. So the idea is to almost look at a robotic system as an ecological system and have heterogeneous solutions emerge. So it's even called robot ecologies. And both me and Ron are really excited about the idea of, if you look at nature, there are fast animals and there are slow animals. So he's going to talk about slow bots. I like them to be called sloth bots, but he gets the last word, so maybe they're called slow bots. But we were interested in sloths, among other things. How can they exist? How come they don't get eaten by jaguars and eagles right away? Why are you so slow? Right. So we got in touch with strangely enough, the world-leading behavioral sloth ecologist, or at least in the US, is a professor at the University of Wisconsin, which clearly is a hotbed for sloths. John Pauli. So he came to Georgia Tech, he gave an absolutely phenomenal talk, and I started working with him, and I learned something interesting. So here, for instance, let's do a little pop quiz. Here is an elephant, a giraffe, and excellent. Wow. Yeah, good copy. We could have picked the other ones, but what do these have in common?
They're animals.
Very good, they're animals. 4 legs, right? They're on the same slide. There are a lot of things they have in common. They eat leaves, that's one thing. They're foliivores. Leaves are super crappy food. They're structurally really, really nasty with these fibers in it, and they're also chemically protected, so they actually have a lot of times poisons on them. So in order to eat leaves, if that's what you eat, you need a gut system, which is like this from John, that's big enough to support this crappy diet. If you're a cow, you can have multiple stomachs, right? So almost all foliivores are large. So they're large and they eat leaves. There's another thing they have in common. They don't live in trees. Because they're large, right? So now, let's say that you're an animal, right? And you have decided that you're going to eat leaves, and you're going to be an arboreal mammal. You're going to live up in the trees, right? Now, you're going to be large because you're eating leaves, but you're going to be small because you're going to fall down from the trees, right? So what this means is you have to be between 8 and 11 pounds, and that's pretty much the sweet spot for this kind of animal. So we have a sloth. This is a two-toe. We have a slow loris and a koala bear. Same weight, same strategy, which is do nothing because the diet is so crappy as much as you can, and then every now and then do things like climb down the trees and go to the bathroom, which is what the sloths do. What I asked John was, why are they doing it? It was just, why would you be slow? And he says, that's the wrong question. You're slow because of the constraints. You have to. That's the only feasible solution if you're going to be a mammal living in the trees eating leaves. So he has this view, which is almost all of biology is constraint-driven. Talking about goals is the wrong thing. Life is meaningless. All you're doing is here's what I think now. All you're doing is you're minimizing energy expenditure subject to a bunch of constraints. So it's an extreme view. Here's the meaning of life equation that I promised you. Right, so sit around, move as little as possible, subject to don't fall down the trees, consume more energy than you use up, mate every now and then, and don't get eaten by eagles. Right? That's pretty much it if you're a sloth. And then all these behaviors fall out. So now, let's see if we can actually take this idea of a controlled barrier certificate and encode this thing in a way that gives us rich, heterogeneous behaviors. The problem is a bunch of constraints means that we need to be able to formally compose these barrier certificates together so that we can do more things than just not drive into each other. So the question now is, how do we go from this via the formal composition or the barrier certificates to something that we can actually mathematize? So technically, a barrier certificate is really, well, first of all, you have to define a safe set, which is the set where the barrier function, h, is strictly positive, and then the unsafe set is where it's less than or equal to 0. Right? And then a controlled affine system renders C forward invariant, meaning you start safe, you stay safe. If you satisfy this differential constraint, and this is just one of these class K functions, I used h cubed in the previous example. But what this ensures is that you will stay there, but you're actually allowed to get up on the boundary, so that's why it's minimally invasive. It's not one of these weird logarithms that you never actually get there. Here you can get to the boundary, but you never mess with it. So this is a barrier certificate. Let's compose 2 of them, right? So I have one which is don't get eaten by eagles, and another is climb trees. So the question is, how do you compose these? Let's say you want to do an and, right? So you have now the red area. Well, it's an intersection, right? And if you immediately jump over to Boolean algebra, the and is a multiplication. So if you're both positive, then the and is positive, that's fine. If you're outside, you're both negative, then this is still positive, so that's bad. So this actually doesn't quite do it. So the way you have to get around this is to say, well, I'm going to define my barrier function to be 0 on the outside. Then the and actually falls off a log. The or, meaning the union, well, you can write it down as an addition, and that satisfies all the right constraints in terms of sign. But the problem is that this doesn't actually satisfy the correct differential or dynamic constraint. This is not just level sets. These are actual things that are going to lead into barrier certificates. So you have to restrict the class of barrier functions you can look at in order for the addition to actually compose. The weird thing about this now, if you have H0 on the outside, is negation doesn't work at all. Because now you don't have a natural notion of negation. This is still an open problem. People are working on trying to come up with a formal, richer way, but we can do ANDs and almost ORs, most ORs. So let's do that. Let's do a quick example of what this would actually look like. So 4 robots, green, blue, red, and yellow. These 4 robots have to, actually what we're doing is we're giving them a bunch of waypoints, so they have to do these waypoints. But they have to be safe. And instead of doing what we did before, which is safe relative to nearby neighbors, they have to be safe. Everyone has to be safe with respect to the blue robot, and the green robot, and the red robot, and the yellow robot. So this is a 4 and. And the green robot has to be connected at all times with the blue robot. The blue robot has to be connected at all times with the green robot. So this is a backbone, communication backbone that needs to be maintained. The red robot has to be connected to the blue robot or the green robot, and same thing for the yellow robot. So now, all we're doing is we say, follow these, go to these waypoints, and then we're giving them these barrier certificates, and here's what it looks like. So this is the path that Guara told the robots to do. And the red, thick red, is the connection that has to be maintained at all times. And again, I really like this because this is complex. It looks really complex, but we didn't tell it to do it. It also looks right, which to me is rare when you get to things like this. Yeah, sure, it works, but this actually looks like the right kind of behaviors emerging. So you see, they're either connected to the blue or the green, the ones that they should, and now they're in a little bit of a problem because this guy needs to get all over there and needs to stay connected to at least one of them. And again, this emerged now directly from the composed barrier certificates. So that's cool. I'm excited about this. This is what I wanted this talk to end with, but we're not quite there. So what I would very much like, and I have students working on this right now, is I want my robots to just sit there out in nature. Or in the robotarium, basically not doing anything, because we now know that life is meaningless. If you're a robot, I think there are other things maybe going on in people's lives, but just sitting there, and then things like energetic states start changing, so all of a sudden you're hungry and your barrier certificate pushes you over to the charging station, or lighting condition changes and you have to go to an area that's better illuminated. So every now and then you have to move in response to these barrier certificates. But most of the time you're just out there in nature doing nothing, which is what most animals do anyway. So that's where we're going. So then having said that, first thing I want to tell you is the Robotarium is indeed open for business. If you're interested and want to try some things, it's robotarium.org. I think these control barrier certificates, they've really changed how I think about a lot of things. Typically you put things into costs. And there is no natural way of having multiple costs together. Should you add them? Should there be a weight? What should that weight be? Constraints are natural, costs are not. And I like that. I think this is a really promising way forward. ONR's wonderful robot ecologies project and the Robotarium actual knowledge. And should point out that if there was something that was exciting, it's probably due to one of these. If you didn't like it, let's blame the organizers. So, thank you.